It works, right? Yeah. Okay, so I need to be close to the microphone, or maybe I can also speak. It's a small room, so I would assume, for your recording, you need me to be close to the microphone. Even if people hear me, it may not be recorded well. Okay. First of all, it's really a great pleasure to be in Korea. Since Tsong-ho graduated and eventually went back to Korea, and gradually I felt more and more connected. I visited several times, stayed a few years ago, multiple weeks in Daejeon as a guest of NIMS. And I cannot say that I feel at home when I come to Korea. I don't speak the language and so on, but I feel as much at home that you can feel when you're out of home. Let's put it this way. So it's a pleasure, and definitely I look forward to more visit, and I hope that I still find host and friends in Korea, and I'm sure that this is going to be the case. Okay, so that's the introduction to my talk. And what about the talk itself? Extremely local wavelet basis, it's the topic. I have a gadget. Let me see that the gadget works. No. That's probably not the direction. It doesn't work this way, and it doesn't work that way. Let me try a little. No, because I'm directing it to this. Now let's talk with this guy. Yeah. Okay, it's a joint work with Young-Mi Ho. It's going to be published in one of the science journals. So let me start at the beginning. So I'm starting with the well-known definition of a wavelet system. I'm looking for that. So we have a finite set of elements in L2, and I'm using here dyadic dilation. That's not necessarily essential, but definitely it's convenient for this talk and for this construction. And integer shifts, and this is the standard definition of a wavelet basis, of a wavelet system generated by those elements that are called the mother wavelet. And we decompose usually that system into scales. So we fix the dilation level J, and then we take all the mother wavelets and all their shifts in the dilation level J. So the full wavelet system is denoted as X of the mother wavelets, and the J scale is denoted as X sub J. And of course, the full system is the disjoint union of the J scales when J goes from -infinity to infinity. Okay, so at the top you can still see the definitions that I put a moment ago. And there are several linear operators that are used in order to... did I push it? Yeah, it went back because I leaned on my laptop. Let me go back. No, I'm going forward. Yeah, I was here. So there are several linear operators that are being used in order to capture basic properties of the wavelet system. One of them is the analysis operator, and which is also used in order to define the wavelet representation. So what is the wavelet representation? You have a wavelet system, and the generic element of the system is X, and you form all the inner product between the functions that you would like to analyze and represent, and all the elements in the system. So that's the analysis operator, and that's actually the wavelet representation, or the discrete wavelet transform. Okay, so again you see it at the top. And now let's start to understand what we are talking about in a slightly quantitative way. So most of the wavelets are in the high scales. In order to understand that, you are saying, no. On every scale, there are infinitely many shifts, finitely many mother wavelets, doesn't matter. So the total number of wavelets at each scale is infinite. But in practice, of course, this is not the case. In practice, you have some function which is compactly supported, and let's say that the wavelet system is also compactly supported, and therefore only the wavelets whose support is overlapping with the functions that you are investigating matter. And if you do that in that way, then since at the high dilation your shifts are actually by scaled integer, as is being denoted here. At the J scale, the wavelets are actually shifted by scaled integers, and there are more shifts, there are denser shifts, and per square inch there are more wavelets. So as a matter of fact, most of the wavelets are captured in the high scale. The higher the scale, the more wavelets there are. So if we are talking about sparse representation, and we are going to talk a little bit about sparse representation, the obstacle are the wavelets in the high scales and not the wavelet in the low scale. In the low scale, there are few wavelets in any case, so they don't pose a problem. And the counting is very simple. If you are in D dimension, D is the spatial dimension, and the dilation level is J, then the number of wavelets at dilation level J is proportional to 2 to the JD. So it grows exponentially fast. And of course, if you want sparse representation, you need to tackle the fact that you have a problem with the wavelet in the high scales. Okay. So here is a topic. So we are gearing in that direction. Sparse representation using wavelet. So we know what wavelets are good for. We know that wavelets provide optimal representation for function with local singularities. Now, I'm talking in an arbitrary number of dimensions. So the spatial dimension is Euclidean space, but the spatial dimension is D. And many of you probably know that there is a criticism, and correctly levied criticism, on wavelet representation, because they say that they are not optimally for representing objects in more than one dimension. Now, and I'm claiming that they are optimal of representing the object in any number of dimensions. So if you don't want to get confused, pay attention to what we are saying here. Wavelets provide optimally sparse representation for function with local singularities. This is correct to any number of dimensions. The issue is that if you go to one dimension, functions with local singularities are pervasive. This is the typical type of functions, and therefore wavelets are very effective in representing a large class of functions. If you go to higher dimension, functions with local singularities are not that dominant. For example, you take natural images, they are dominant by the edges, and not by the local singularities. Because of that, wavelets are not that optimal. But the claim here is a correct claim. So they are optimal for representing any function that has only local singularity. Local singularity in the sense that it's a single point, the smoothness of the function is of a lower class, and elsewhere the smoothness function of the function is at a much higher class. So in what sense they are representing the local singularity in an efficient way? So look at the bottom of this transparency. So the sense is that if you go up in the scale and you look at the large wavelet coefficient, because how do you get a sparse representation? The coefficients are not going to be zero. You take a function with local singularities, and you compute the inner product between the function and the wavelet system, and almost all the coefficients are non-zero. But most of them are very small, and you threshold them, make them zero, and you retain only the large coefficient. So the question is, how many large coefficients you expect to have? And the key in the success of the wavelet representation for local singularities is the fact that the number of large coefficients per scale is fixed. Now go back and remember what I said 2 minutes ago. If you go up in the scale, the total number of wavelet coefficients grows exponentially fast. But if you have a function with local singularity and you retain only the large coefficient, the coefficients that you retain as you go up in the scale, they are fixed in number. They don't grow in their number. And that's the effective way that the wavelet represent local singularities. So you can see it as 1 and 2 in the transparency. A fixed number is large and being retained. All the other coefficients, because the ambience domain of the function, it is very smooth in that domain, all these coefficients are going to decay very fast, and eventually are going to get thresholded. Okay, so this is a repetition of what we said so far. And so let's see what are the classical challenges when we try to build a wavelet system that is effective in one dimension or in multi-dimension. So that's what you see here is the repeat definition of the wavelet system. So I listed here 4 items. I'm going to ignore that item because that item is how shall I say, the litter bins that collect everything that is not listed in the first 3 items. So there are really 3 items that are the key issues in building a successful wavelet system. So the first one is the fact that you would like the wavelet system to be supported by fast algorithm. You need to be able to compute fast the decomposition, and you need to be able to compute fast the inverse, namely the reconstruction. Now, this is probably the reason that wavelet exploded about 25 years ago. Malak came with his thesis, and in his thesis he presented fast algorithm for computing the wavelet representation, linearly fast algorithm. That made, said that as a matter of fact in engineering application there's something feasible, and it exploded within 3 or 4 years. Wavelet became a household name. I'm not talking here about the algorithm, so I'm going to focus on the two other issues that are complementary and competitive one to the other. So when we talk about the wavelet system, it's one of the several paradigms where we try to be local simultaneously in frequency and in space. So we want, as a matter of fact, when we look at a single wavelet coefficient that comes from a certain mother wavelet, from a certain dilation, from a certain shift, we would like to say that the coefficient is seeing that information in space and that location in frequency. Like in music, that we play music, we hit the music key at a certain time, then we know that at that time we hit the key, and we also know what note we played. The note is the frequency, and the time that we hit is the time. That's local in time and frequency. So there are ways to measure how local the wavelet system in time, and there is also, that goes under the notion of local here, number 2, and there is a way to measure, a more sophisticated way to measure how local we are in frequency. It goes in my talk under the notion of performance, and we would like to optimize those simultaneously. And the problem in high dimension is that it's very hard to optimize the localness in time while preserving reasonable performance. So I will define later on what performance is. That would take me a bit of a work, but I'm going now to define for you what does it mean to be local in time space. Okay, so let's move on and see that. So how to measure local in time space, that's what I just said. Okay, so here is the way I'm going to measure in this talk, and that's definitely one of the acceptable ways to do so. I will take all the mother wavelets that I have in my system. That's denoted by a capital psi. I will take the support of each of the mother wavelet. I compute the volume of each of the support of the mother wavelet, and I will sum up those volumes. Why it is a suitable way to measure the localness of a wavelet system? Because if you take a generic point in the space domain and you take a fixed scale, you fix the level J of the level of dilation in the wavelet system, then these numbers that you see over there, that I just defined over here, show you the average time or the average number, if you take a generic point in your time domain, that on average this point is covered by the support of these many wavelets in your scale. So these are these many shifts of the mother wavelets that are going to contain in their support your generic point in the domain. So it's a good way to measure localness. If you followed me, that's good. If not, that's definitely an acceptable way to measure localness in space and time. Space, because we are in more than one dimension. Okay, so the first natural question is why it is not moving ahead. That we solved. So the second natural question is, how local are standard wavelet systems? Okay, so you are not going to be local, the localness, this L of psi, is not going to be less than 1. Because if your wavelet system, for a generic point in the space domain, there is on the average less than 1 wavelet that contains that point in its support, then the wavelet system cannot see the entire space domain. There are missing information there. So the minimum, so in function, in analysis, in mathematical analysis terminology, that means that you are not going to be fundamental. Namely, you are not going to, the span of the wavelet system is not going to be dense in L2. So that's a necessary condition. So it's going to be greater or equal 1. Can we be, so the optimal, the epitome of localness is 1. So can we meet that optimum? Yes, the Haar system in one dimension, its localness is 1, but its performance, namely its localness on the frequency domain, is completely abysmal. So if you really want to stretch it to the bottom, then you will get very local in space, but you are going to be horrible in frequency. So here, are we moving? Yeah. Okay, so let's go to higher dimension, and we want better performance. I yet to define what performance is. So for example, let's take a practical system. Practical system, I'll go to 4 dimension. That's, for wavelet system, is reasonably high in terms of the number of spatial dimension. And later on, when I define performance, you'll see that the leading notion in the context of performance is the notion of vanishing moments. And I'll take 4 vanishing moments, which is the, how shall I say, the most used systems in practice usually would have 4 vanishing moments. And I will choose probably the most used system in this regard. It's called the 7-9 system. It's a system that go according to the bioorthogonal construction of Dobshi, Cohen, and Fauveau from 20 years ago. Okay, how local the system is. Take all the mother wavelets in the system, compute the volume. We are in 4 dimensions, sum up all the volumes, and let's see what the number is. So the number is 40,000. So what does it mean, 40,000? 40,000 means that if you take a generic point in your 4-dimensional space, and you fix the dilation level, there are about 40,000 different wavelets, different shifts of the mother wavelets and their shifts that are going to cover that point. You're saying, so what? Well, if you write all kinds of mathematical theorems, those mathematical theorems they are usually geared at the asymptotics. They are saying, when J goes to infinity, when this goes to infinity, then this and that happens. And they are constant in those asymptotics. Those constants are going to depend on the localness. And the constant are going to be amplified with localness is 40,000, then the constant is going to reflect the fact that the localness is 40,000. And 40,000 is not local at all. And if I go above the dimension, that number is going to grow exponentially fast if I go up in the dimension. So if I go to dimension 10, probably we are not talking about 40,000, we are talking about a few billions or a few trillions. And that's not local. I did not say, by the way, I said 7-9. So maybe I'll spend another minute explaining here something. Look, if you want to do a construction of wavelet system in high dimension, you need a methodology for doing that. So you are not going to go to the high dimension and do some intrinsic construction because it's not going to work. Just to give you the idea, if I go to dimension 10, and I want to do an intrinsic construction of a wavelet system in dimension 10, I will need a minimum of more than 1,000 mother wavelets. Otherwise, I will not be fundamental in L2 if I'm compactly supported. And if I do intrinsically, I need to give you a definition of 1,000 mother wavelets. So people don't do it that way, of course. What they do, they are trying to build some simple rules, and to use these rules in order to build system in all dimensions. The simplest rule is to take a one-dimensional system, and the 7-9 is a one-dimensional system, and to use the so-called tensor product, which essentially you are multiplying, you are building a function in 4 variables, a tensor product of functions in 1 variable. And that construction is the construction that I'm referring to, and the localness numbers are reflecting what I just said. Okay. Let me move ahead. I think that I spent so far 20 minutes, that's almost half of my talk. I probably will not be able to cover all the details of the construction itself, but definitely I will be able to show you something about that construction. So this is not local at all, and we are trying to do better, and I'm claiming today that we can do much better. And I will try to revisit in a moment this, how shall I say, a case when you are in 4 dimensions and 4 vanishing moments, and what localness we are going to have. What localness? Look, if the systems that I just referred to, its localness is 40,000, and I can reduce it to 10,000, I would not have been standing today and claiming that I have something to share with you. And the last one at the scale is 0.1, and I told you before that if you go below 1, you are not fundamental in L2. That's impossible. And also, we are not going to get to 1. Usually, you try to get as... So I show you some numbers, and later on we'll see how far we get that down. Just to give you a little bit of understanding, if I try to take a system whose performance is abysmal, like the Haar wavelet in 4 dimensions, it has only one vanishing moment, which is as low as possible, and the localness of that system is 15 in 4 dimensions. It's always 2 to the number of dimensions minus 1 for the Haar system. Okay, in order to give you a little bit of insight, I need to define finally performance. So let me spend the next 5 to 10 minutes and explain to you how we measure performance. There are many ways to measure performance along the lines that I'm showing you now, but all of them coalesce at the end at about the same location. Performance is being captured by trying to understand how well the wavelet system is doing in terms of capturing the exact smoothness class of the functions that is being investigated. Now, I'll give you the details here, but for those of you who have not seen it before, it's probably is going to be better to look at the big picture, at the qualitative level of the discussion, and not at the details of the various definition and the various expressions. So I need to start with a smoothness space. I've chosen here the L2 Sobolev space, but you can do a different scale, and essentially the definition would not change in any dramatic way. So this is the Sobolev space of L2 functions with smoothness alpha. This is the homogeneous Sobolev space, and this is the standard definition. And associated with that, I'm defining a discrete space of coefficients. If you remember, in the wavelet system, there is a dilation that is denoted by J. There is a translation that is denoted by K. So those would be the wavelet coefficients that correspond to a given function. I will take a given function. I will compute the inner product of this function with the wavelet system. And I will index the coefficients that I get in this way by the dilation and by the translation. And since I will have several mother wavelets, I will have to do it separately for each mother wavelet. And then, because I anticipate that my underlying function comes from a certain smoothness class, I will penalize the coefficient in high scale. This is J is the scale. I penalize according to the smoothness that I need. And if you don't want to follow, then I'll give you the gist. I'm building a discrete sequence space so that it is true that if the function belongs to a certain smoothness class, the Sobolev's class of dimension alpha, of the Sobolev's class L2 of smoothness alpha, then the discrete space, the coefficients, the wavelet coefficient of that function should belong to that discrete space. Okay, so I have now a way to say whether the wavelet is doing the job. What does it mean whether the wavelet is doing the job? I will take a function from the smoothness class. I will compute all the wavelet coefficients of the function, and I will compare the norm of the function in the smoothness class to the norm of the discrete coefficients of that function. And I know that if the wavelet is performing well for this smoothness class, there would be a connection between the standard smoothness class of the function and the computation of the L2 norm of these coefficients. So here is the first definition. I need to assume that my wavelet system is a frame, and I'm not going to define here a frame, despite the fact that it's already being defined several times in lectures that I heard here. And we are going to do the following. We are going to take a function in L2 and measure, first of all, the norm of this function in the smoothness class. Of course, if the function is not in the smoothness class, this is going to be infinite, and therefore the condition here is vacuous. If the function is in the smoothness class, this is a finite number here, and there is a condition here. So what is the condition here? The condition here is that if you compute the wavelet coefficient of this function, that's the analysis operator, it computes the wavelet coefficient, and then you compute the norm of the wavelet coefficient according to this definition, then the norm of the wavelet coefficient would be bounded independently of the function f by the smoothness norm of the function up to a certain constant. And if this is the case, we are saying that the wavelet system provides performance at that level, at level alpha. And the full performance of the system, according to this definition, is the supremum of all alpha for which this inequality works. But this is only one side inequality, and that's what we refer to as the Jackson-type performance of the system. It looks very challenging to measure the performance, but we know what characteristics of the wavelet system are going to deliver performance. And I will say it here at the bottom. It is being said explicitly that the Jackson performance, the maximum smoothness according to that definition, is essentially defined by the vanishing moments of the system. And for those of you that don't know what the vanishing moment of the system is, it's the highest number of moments such that all these moments with respect to all the mother wavelets vanish. And you can see that definition. Okay. And there is a complementary performance, which is called Bernstein time performance, where you take the same inequalities that you had before and you complement it by the converse inequality. And in this case, the wavelet coefficients are going to give you an equivalent norm for the Sobolev norm of smoothness alpha, and you ask, how far can I push alpha? And the wavelet coefficients are still going to give me an equivalent norm. Now, if you didn't follow that completely, and there is a little bit of discussion that the Bernstein performance is not visible by the wavelet system, you need to build a dual system and you need to analyze the dual system. Look, put all that aside and focus on the essential. There are two numbers. One is called the Jackson performance and one is called the Bernstein performance. And every wavelet system that you will come up with, I can associate with these two numbers, the Jackson performance and the Bernstein performance. And in a very qualitative way, those two numbers show how local, in a very mathematical way, how local the system is on the frequency domain. So, on the one hand, I have localness on the time domain. The smaller the number is, the more local I am on the time domain. And the optimum is 1. You never go below 1. And on the other hand, I have localness on the frequency domain, and there I'm pushing it up. I want higher performance. I want to characterize more and more smoothness classes. There is a Jackson performance, there is a Bernstein performance, and if I want to be local on the frequency domain, I want these numbers to go up and up and up. So the optimal wavelet system, its localness in time is going to be 1, and its performance in frequency is going to be infinite. No such system exists. So we need to start to compromise how far we are going to push the performance up and how much we are going to take to get the price by pushing the localness in space up as well. Okay. So here is a summary of requirement. I want a wavelet system that is highly local in space, has high Jackson-Bernstein performance, and I also want it to be a risk basis. And I hope that all of you know the notion of a risk basis because I'm not going to define it. So I could compromise by saying that I only want a frame, which is essentially a redundant risk basis, but then I will get different construction. We also have constructions of frame in this regard. Okay, so what you see here is a table that captures some essential issues with our results. So we have a theorem, and based on this theorem, we have an algorithm. And based on this algorithm, we were able to derive a complete class of functions. What does it mean, a complete class of functions? It's in any number of dimensions, and I can get to any Jackson performance that I would like. I can push the Jackson performance as high as I want, and I can push the Bernstein performance as high as I want by fine-tuning my construction. So you can see that I'm starting at low Bernstein performance. For those of you who know wavelet system, these are the vanishing moments, essentially the vanishing moments in the system. And I can go all the way to 14, which is very exceptionally high for a wavelet system. And this is the dragging below Bernstein performance that also grows, but doesn't grow that much. And for example, over here, it means that the dual system is already 3 times differentiable, continuously differentiable, all the mother wavelets. And now the question is, if these are the performances, what is the localness of that system? And you can say, well, at what dimension? First of all, the localness does not grow with the dimension. And here are the localness numbers. So you can see that the localness numbers are only 1 above the Jackson performance. So if you want now to compare that to what we have seen a moment ago, this is true at any number of dimensions. Okay? I'll go over here, 4 vanishing moments, and smoothness 1 is essentially equivalent to the 7-9 systems that you've seen over there. The 7-9 system, its localness was 40,000 in 4 dimensions, and it grows exponentially fast. In our system, the localness is 5, bounded by 5 in all dimensions. Okay, so that's the comparison. And remember that you cannot go below 1. And look at the numbers. In all the dimensions, these numbers are relatively small. And of course, they are not 1, but they are not explosive compared to the complete optimum. So how actually we are doing that? I'm left with, let me calculate, I left with about less than 15 minutes. So I was very slow on that part because this is the part that I want as many of you to understand. I will go pretty fast on the part of the construction because A, I'm not left with too much time, and B, only the experts among you that know in and out wavelet system will be able to follow that part, even if I spend a little bit extra minutes. So let's see what we are going to do here. So we have 2 algorithms for doing the construction. And the numbers that I gave you back then are based on the algorithms that provides a more local construction compared to the other one. So I'm presenting you the gist of one of the general methodologies to build systems that are as local as what you have seen. So I'm starting with the fact, first of all, pay notation to the following. The number of mother wavelets that I need to construct in D dimensions is 2 to the D minus 1, if I want a Riesz basis. So I'm taking the vertices of the unit cube, and the number of vertices of the unit cube is 2 to the D. I removed in the origin, I have 2 to the D minus 1 vertices. So I'm going to index my mother wavelets by the set E. And that's very common. Many people who do construction in D dimension are indexing in that way. To this end, I'm building a map from the vertices of the unit cube into the integers 1 to D. D is the underlying dimension. I call this map R. There is one condition on the map R. The condition of the map R is that if you take any vertex from the unit cube and you compute the entry, of course, the entries of that vertex is either 1 or 0 because it's a vertex of the unit cube, and you compute the entry of that vertex whose location is R, because my map is to the number 1 to D. So it's a variable. It's an index of a variable. You compute nu at that location, you get 1. Okay. There are many maps that can do that, so I need to choose one of these maps. For example, in 1 dimension, I have only 3 vertices of the unit cube. The vertex 1, 0, the vertex 0, 1, the vertex 1, 1. The vertex 0, 0 was removed. And according to the condition here, I must map, and the R is going to map into 1, 2, because I have only 2 dimensions. So according to the definition over there, I need to map 1, 0 to 1, and I need to map 0, 1 to 2. And 1, 1 I can either map into to 1 on 2. Okay, it's a map that I need to fix, and I can always construct it, and I have some flexibility in how to construct that map. Let's say that I fix it and I have it. Okay, the next step is to choose a refinable function that I denote as phi sub c, and I denote the mask on the Fourier domain, namely it would be a trigonometric polynomial mask as tau sub c. And in order to get as local as in the constructions that I refer to in my transparency, you should choose the support function of the unit cube as your refinable function. And then the mask is a very simple trigonometric polynomial. And then I'm going to step number 2. Step number 2 is the critical step in the construction. What we do now, we choose a univariate trigonometric polynomial that I denote as tau. Univariate. And I need to do it in many dimensions. That's the critical component. We are not going to do something intrinsic in high dimension. Somehow we are going to do it in one dimension and push up. Okay? So that trigonometric polynomial that you see is, the trigonometric polynomial has only one condition. If you shift it by pi, you get minus of the trigonometric polynomial. Think about exponentials. This means that all the exponentials in the definition of the trigonometric polynomial has odd frequency. If you cannot take a trigonometric polynomial with even frequencies, otherwise you will violate this condition. Okay. And then, look, this is a univariate trigonometric polynomial, and I'm going to do construction in d dimension. What am I going to do with this univariate trigonometric polynomial? I'm going to lift it to high dimension, but I'm not going to lift it by tensor products. That's exactly the curse that we've seen back before of losing the localness. I'm going to lift it by simply taking the variable, the univariate variable of the trigonometric polynomial and saying, you are in d dimension, you are in 2 dimensions, say. So instead of thinking about you as a univariate variable, I will think about you either as the first variable in 2 variables or as the second variable in 2 variables. And this is what you see over here. What you see over here is I have d different liftings of my univariate trigonometric polynomial by saying, hey, the lifting, this omega is in d dimensions, take the univariate polynomial and think about the argument as your univariate polynomial as one of the variables in d dimension, and you have a choice how to do that. So the trigonometric polynomial, say in 2 dimensions, you are either aligning the Fourier coefficient of the trigonometric polynomial horizontally, or you are aligning the Fourier coefficient of the trigonometric polynomial vertically. In higher dimension, you have d ways to do it. But the lifting is not changing the number of exponentials that are being used in defining the trigonometric polynomial. If the univariate trigonometric polynomial used 4 exponential, all the lifting are still using 4 exponential. It's not tensor product. Okay, this is step number. And then I'm defining the mother wavelets. So let me show you now. I'm closing to the end of my time. No, I still have about 7 minutes. Okay. So here is the way the mother wavelets are being defined. So let's see the definition. The usual definition of mother wavelets go to the Fourier domain. That's one of the ways to define the mother wavelet. And this is a standard way. You define a dilation of the mother wavelet by taking the refinable function and multiplying by some trigonometric polynomial. So the key is not to put attention to this expression. That's the mother wavelet indexed by nu. By the way, my mother wavelets are indexed by the vertices of the unit cube, if you still remember that. So this is take a vertex of the unit cube and define one mother wavelet. So the mother wavelet is defined standard in this way. So the only thing that I really need to pay attention to is what trigonometric polynomial I have over here. Okay, this is just a scaling parameter. Forget about it. This is the exponential with frequency nu. Nu is that integer, which means that if you go back to the time domain, modulation on frequency is translation on the time domain, which means that it's some translation. There is some other wavelet and I need to translate it in some way. That's not essential. It does not change the support of the mother wavelets. So the key is in this expression over here, because this expression over here is going to show you how large is the support of the mother wavelets that I'm building here. Because what is going to happen, as a matter of fact, that in the space domain, you are going to take your refinable function, you are going to shrink it by a factor of 2, and you are going to translate that shift according to the Fourier coefficients that are going to be captured in this definition. And there is another shift over here, but a single shift is not going to change the support. So how many do I have over here? I take my trigonometric polynomial, I lift it in some of the ways, and it doesn't matter now to pay careful attention to this R of nu. Conjugate is nothing. That expression over here, the number of exponential in that expression is exactly the number as exponential in my original trigonometric polynomial. So it's some fixed number that intrinsic to my construction. It has nothing to do with the spatial dimension. And you need to add one more because there is the constant one here. So the total number of translates that are being used over here depends only on my choice of the trigonometric polynomial. Is the number of exponential, the number of steps in the trigonometric polynomial plus 1 because I have a constant here. Okay, so think about the refinable function as the support function of the unit cube. Okay, the volume of this function is 1 in all dimensions, of course. You shrink it by a factor of 2, the volume is 2 to the minus d. Okay? How many mother wavelets I have? About 2 to the d. So if I take the contracted refinable function and I multiply by the number of mother wavelets, I get 1. So why do I get more than 1? Because each mother wavelet is going to be shifted by how many number of shifts, depending how many steps are in this trigonometric polynomial. The number of steps in this trigonometric polynomial is independent on the dimension. It depends only on the number of steps in this trigonometric polynomial, and you add 1 to that. And that's what you are going to see in the next transparency. Okay. If I list it as V, the volume of the support of my refinable function, and I took the refinable function that is going to give me volume 1, then the total localness that I'm going to get is the volume of the support times the number of steps in the trigonometric polynomial plus 1, divided by 2 to the d because I dilate my refinable function, multiplied by the number of mother wavelets. And now, sure, you need to move. Okay. If I take the support function of the unit cube, then this is 1, and this is smaller than 1, and therefore my localness is always smaller than the number of steps in the trigonometric polynomial plus 1. So I showed you the localness, and what I'm going to miss is the essence. The essence is that I was able to construct something that is very local in space. But who says that I get any good performance? How well I am in the, how local I am in the frequency. First of all, I need to argue that I get a risk basis in this case. That's also non-trivial. But more important, even if I get a risk basis and my performance is not good, I didn't do anything good in this regard. By the way, some of you may think that because I'm using piecewise constant, look, if the refinable function is the support function of the unit cube, then my wavelets are piecewise constant. So, well, but piecewise constant are known to have poor performance. They are not local in frequency. This is not correct. This is entirely not correct. This is a misperception because the decomposition system does not need to be smooth. The reconstruction system needs to be smooth. And the reconstruction system is not visible in this algorithm. And the reconstruction system is smooth. Otherwise, we are not going to get performance. Okay, so ensuring a risk basis. Okay, so there is a theorem here. I will just go very fast through this theorem, but I'll tell you the essence of the theorem. The theorem is taking the constructions that you've seen before, which is very explicit and relatively simple, and says that I can derive the performance from this construction and tell you, if you take, in this construction you choose only one thing, the trigonometric polynomial, the univariate trigonometric polynomial. That's the only thing in this construction that I can vary. So give me the trigonometric polynomial, I will tell you what the performance of the wavelet system is. And there is a little bit of something here that says, start with your support function. Take the trigonometric polynomial, add 1. Do something in d dimension. Take the guy in t dimension, periodize it, divide it here, and divide it there, and divide it, and divide it. There is a whole theorem that says that is going to be the performance if you follow all the rules here. And of course, if you could prove a theorem like that, then the next step is to say what trigonometric polynomial you are going to choose in order to get high performance. And we found trigonometric polynomials, then you need to work hard according to that theorem to prove that what performance you get. And that would give you the numbers that you see, the tables that you see back then, with the Jackson performance, the Bernstein performance, and the localness. The localness I showed you how to do. And the performance is this theorem plus a little bit of a work. And I think that the next transparency is the transparency that you were waiting for for 45 minutes because it says that this is the end. Thank you very much for your attention.